Cool. All right. Yeah. So DC motors, how do they work and how do you control them? Is the what we're going to do. So yeah, we'll go through how brush DC motors work, DC motor behavior, so stuff like how torque and speed change with voltage and current and that sort of thing. How to control a brush DC motor. And then we'll move on. Oh, there's a new bullet point in here that's not there. Aiden's going to talk for about 10 minutes on how to pick a motor and the gearbox combination, how to shop for them, basically. Sort of a brief summary. There's a longer version on Nuclear of that. And then we'll go into how brushless DC motors work, how to control them, which will be sort of a 6-parter. And by the end of it, you'll understand what the hell that block diagram is. I promise you. So it's all happening. Yep. Hopefully you've brushed up a little bit on Lorentz force and Faraday's law if you haven't done electromagnetism before. But hopefully most of you have done some physics at some point and have covered that. Like I said before, please interrupt if you have questions. I want this to sort of be a bit of a two-way street. So yeah, no dumb questions. Fire away whenever you have any queries. All right. Yep. So we'll just touch base on the Faraday's law and Lorentz force. If you've got a current moving through a wire in a magnetic field, that wire will experience a force perpendicular to the current and the magnetic field. That one's probably the easier one. It's probably the one you're most familiar with. Faraday's law is a bit more weird. We'll only use this briefly, so it's not the end of the world if you don't understand it. But if you have a change in flux through a wire, that will generate a voltage in the wire. So that change in flux can be magnetic field, or moving into a magnetic field, or moving normal to a magnetic field, or something like that. Yeah, any questions on this before we go? This is quite important to how motors work. Cool. All right. First off, brush DC motors. These are very simple in comparison. Actually, they're actually more complicated in comparison to brushless motors, but the parts are fairly similar. The two, if you get anything away from this slide, it's what a stator and a rotor is. So the stator is stationary and the rotor rotates. Now, but what they look like is very different on a brushed versus a brushless motor. So on a brushed motor, the stator has the magnets on it and the magnets don't move. The rotor has the coils on it and the coils move. And this is the opposite in a brushless motor, as you'll find out later. Yeah, and then you've got the commutator, which is over here, that interacts with the brushes, and as the shaft rotates, the current connects through the coils in a different direction, which changes the current through the motor itself and changes the force. I'll go into that in more detail in a second. And then finally, you've got the magnets, which are these big gray sort of arcs on the outside. Cool. So that's that. So sort of to build up how a brushed motor works, we'll start with a simplified model. You've probably seen this in like a year 10 or 11 physics textbook. There's only one coil and the commutator has only 2 segments. And as you can see, so current is flowing. You can probably just see the light blue arrows, current's flowing through the coil from the commutator. And you can see when the commutator switches sides on the brushes, the arrows switch directions. So the arrows are pointing up and then the red arrows are pointing down, which means that as the coil rotates, you get a torque pulling one way, and then right as that torque goes to 0, because the arrow is coincident with the coil, you then flip the direction of the magnetic of the force on the coil, which pulls it down the other way. Does that make sense? That wasn't a perfect explanation. Cool. All right. So yeah, this model is very helpful for kind of understanding the forces at play and how the Faraday's law, the Lorentz force works in a motor. But it has very obvious problems. So at the bottom, when your force vector is coincident with the coil, there is no torque because the force is in line with the rotation. And obviously in this image right here, you've got the 2 parts of the commutator are shorted across the brushes. So you just get like an instant short and your motor would just smoke and do nothing. So it's great for learning the theory, but it doesn't work in practice. So then we move on to level 2. Now this is a little bit more complicated. There are now 3 coils and still 2 magnets. There are sort of 2 ways to do it. You can do it in this delta configuration, which I think is more common, or this Y configuration. So if you've done like 2131 with all the power electronics, the coils are actually connected together in a delta or a Y. And what this means is that the brushes are always in contact with at least 2 commutator segments. So there's no dead spots on the commutator like there was in the first one. Now the way the current flows through is a bit. This video is helpful, but it's probably a bit hard to grasp in like the 2 minutes that we'll be here. But you can see, for example, the positive side of the brush here is connected to this node of the delta. You guys can see my mouse, yeah? Yeah, cool. And the negative is connected to this node here. So the current's going to flow through this coil and generate the magnetic field. These north-souths in here are not actually magnets. They're just there for illustration. So it flows through this, but it actually also flows through the other 2 in the opposite direction. And it just so happens that the magnetic fields generated in the correct direction, that you always get the torque pulling you in the right way. So all 3 coils are actually being used at the same time, and they're all pulling you in the right direction. So it's quite interesting. And then, of course, if you have the case of the brush that's shorted across the 2 commutator segments, it's just all you have is these 2 nodes are now the same voltage. So you still end up with current flowing through the other 2 coils. So you just don't get anything through this one coil. All gravy. Any questions on that? Any confusion? Yeah.
So those magnets, is that just representative of the induced magnetic field from the current flowing through that coil?
Correct. Yeah. So these 2 big ones on the side are the permanent magnets, and then so yeah, in this one you have a magnetic field pointing inwards, generated by the coil, the current through the coil.
So that's going to change depending on as the motor spins, right?
Correct. Yeah. As the commutator
directions, yeah.
Yeah, as the commutator segments connect and disconnect, it'll change which direction. It's always pointing in the correct direction to create the torque.
And does the torque always happen to act on the induced magnetic fields sort of at right angles?
So it won't be right angles perfectly, because if we go back to the example here, it's only right angles at like one position. But you'll always have a component that's in the rotation direction.
Also, so it avoids the bottom diagram. Correct.
Well, you might have one coil that's in this configuration, but the other 2 will always pull the other way.
Mm.
Yeah. So there's sort of 2 ways to think about it. I sort of glossed over it at the start. You can picture like the current moving through the wire and then a magnetic field, and that enacts a force. Or you can think about the generated magnet from the coils attracted to the permanent magnet. And that'll be a useful analogy later when we move on to brushless motors. Cool. So yeah, as you can see, as you were saying before, Matt, you can see the arrows on this, the black arrows flip direction on the coils as they commutate with each segment. This might be a helpful thing to sort of come back to later and just stare at for like 5 minutes until you understand it. Alrighty. Lastly, just briefly, in practice, brush motors can be even more complicated. So you can see there's like way more than 3 commutator segments here, and there's I think like 6 coils. The detail is not that important, but it just means it's basically smoother, I think. Yeah. Cool. Over to some mathsy stuff. So the most important thing is that V does not equal IR for a motor. If you ever apply V equals IR, you'll have a bad time. the most sort of accurate way. The other thing is none of these equations are right, is what I'll say to begin with. They're all models and they will get you most of the way there, but not completely. The easiest way is to picture this. So you've got a resistor in series with an inductor in series with a voltage source. In principle, you can kind of combine the voltage source and the inductor together. They kind of do a similar thing, and we will make that simplification in future. But essentially, if you like measure the coils of a motor, you'll get something around like 2 to 3 ohms, like in that ballpark, like single ohm digits. And so if you dump like 30 volts across that, you're going to get a lot of current, and that's where the inductive part comes in. And essentially, the inductive part will resist the change in current. So you get the voltage is LDIdt. So if you turn on your voltage, your like power supply, the current will take some time to rise up in this like first order response. So it's sort of like a capacitor charging, but the opposite. So instead of the voltage slowly rising up for a capacitor, it's the current slowly rising up for a motor.
Well, I have a question from the previous slide. I think my mic wasn't working at the time.
Yeah.
So yeah. So that one is showing the delta configuration.
Yes.
When the brush is right in between 2 segments of the commutator, does it contact neither or does it contact both?
In short, it doesn't matter, but it can contact both. We'll say it contacts both, because if it contacts neither, you'll have it stop. You have a dead spot. So if it contacts both, then these two nodes will be the same voltage, and then the current will still flow through the other 2 coils.
Yeah, thanks.
Yep. Cool. All right, back to this. Lastly, the back EMF is proportional to the so this VEMF term is proportional to the velocity of the motor. That will come in handy later. I probably won't go into too much detail as to kind of what that means. You can look up a lot of stuff on this if you want to. Unless Christos, you want to add anything?
Yeah, I think you'll go into more detail later, but like from that, you can see that voltage, you kind of just consider a DC disturbance when you're controlling it. You basically ignore the back EMF and you just treat it like a current, and that current will be proportional to torque. But yeah, you go over that more later.
Exactly. We'll get to that in a sec. But in principle, this back EMF is also proportional to the current that's going through the coils. So it's all of this and a whole bunch of other things. So this is why it's such a simplification. But in principle, it's good enough. Cool. This is a very important slide, the electrical to mechanical power equation. You have your voltage and your current going into your motor, and you have your power and torque coming out of your motor, times some efficiency, which will be less than 1. So for those who are on the electrical sub team, you may not be super familiar with mechanical power, but you multiply the speed of your motor by the torque it's putting out, and that gives you the power. Very important.
Wouldn't the efficiency have to be more than 1 here? Otherwise, you're getting more mechanical power out.
Maybe. Sure. If it works, it works. I don't know.
Okay.
Whatever
Which becomes the input side. Never mind.
No, yeah. Anyway, yeah. Cool. Lots of text on this slide. A couple of general rules of thumb. If you have a consistent voltage across your motor, if you have a consistent torque loaded on your motor, so no torque or some fixed value of torque, the velocity of the motor will be proportional to the torque. To the voltage. Let me say that again. The velocity of your motor will be proportional to the voltage. So as you increase the voltage across your motor, that will increase the speed it spins at. And that's a linear relationship, give or take. And if you want to slow down the speed, say you've got a 30-volt Rover battery and you need to slow down your motors, you then PWM that, which reduces the effective voltage across the coils. And that will slow it down. The other one is that with a consistent voltage, current is proportional to torque. Now, sometimes you'll see that torque is proportional to current, and that's also true, but the cause and effect is that the current increases when your torque increases. The current is driven up by the torque being driven up. So you don't supply more current to get more torque. The torque, like on your motor, is increased. Say you're driving up a hill, the torque will be increased, and therefore your current will go up in order to supply that torque. So yeah, you don't have direct control of it. The motor will draw what it needs, and this causes problems. This is why you need current limiting and fusing and stuff, because the motor will happily keep drawing current until it or the rover explodes. So yeah, any questions on those two? They're quite important.
That can be a very confusing concept to get, the velocity and voltage and the torque thing. The easiest way to think about it is actually if you go back and look at that equation from the previous slide, right? One more actually. So if you've got your V supply is proportional to the rate of change of your current, if we ignore resistance, the only two things that contribute to the voltage in that loop are the rate of change of your current and your back EMF. So if you're at a constant torque, so a constant current, then that LDIDT term contributes nothing, and the voltage you have to supply is just the EMF, the back EMF, which is just proportional to velocity. So that's why the current doesn't really have an impact. But then if you do want to like accelerate and you increase the torque, then that will require voltage to change the current, which is why it only works at consistent loads. But yeah, and if the load is consistent and the current doesn't need to change, then your supply voltage equals your back EMF.
Yeah, and it's probably a good time to remind you that Ohm's law does not apply. So you might be thinking, oh, voltage and current are just proportional, because that's how your brain's, like, that's how you're taught to think about it for so long. But no, they are completely decoupled quantities in a motor. Well, not completely, but like they're not linear like you're used to them being. So that's how you can have independent control of your torque and your velocity.
I was going to ask, is like the back EMF then and the supply voltage, are they basically in equilibrium when the motor reaches its velocity?
Yes,
Yep.
I think so. Yeah, there's a lot of different ways you can think about what's going on mathematically behind the scenes. So yeah. What is back EMF? So I think I have a slide in more detail when it comes in handy, Tal. So just sit tight. That we use it in brushless control, and I have a slide explaining it better there. So don't have to wait long.
Is it possible to current control a motor and like set the current and then do voltage limiting, and then have the velocity just be chosen by the motor, and then that sets the voltage?
Yes. Yeah. So if you have a current, if you have a current controlled power supply with some voltage limit, if the torque is really high, it will slow. Or yes,
So
but okay. The answer is yes, but it doesn't really make any sense, because the current won't be at the limit unless the torque, because the current's driven by the torque, not the other way around. Does that make sense?
So if you were to like run more current through the motor than the torque currently applied, it'll start accelerating the load. That torque, it'll still produce more torque, but that torque will go to accelerating the inertia of your load, and then it'll speed up. So you kind of can, but like it'll change the velocity by doing it like that.
Yeah.
And just asked, is power control via motor described by a change in voltage experienced by the motor? Do you mean current control, Aiden?
So when we change the PWM input effect, like the effective voltage, if we put that into our equations, doesn't that mean that like it's like torque is proportional to voltage, not current?
No. So if you PWM it and reduce the speed by half and then apply a load to the motor, it will still draw more current to supply that torque.
Okay.
Yeah. Now
I don't think that happens in practice.
the stall current will be lower because at stall it is a resistive load. But yeah, so it won't reach as much torque, I think. But you wouldn't be wanting to be operating in that regime anyway, because it'll probably damage your motor.
Okay,
Yeah.
so everywhere except close to stall is similar though. It just takes more current to get to the same torque.
So close to
It's-
stall, so what stall current is when basically your current hits that RI limit. All your voltage is going into that RI term of the differential equation. So none of it's going towards anything else. There's no back EMF because it's not spinning and you can't change the current anymore. So as you get closer to stall current, that RI term starts becoming more and more important, just like the resistance of the coils. And then it stops behaving in this nice torque is proportional to current way, because then Ohm's law comes back into play, and adding more current to the motor drops the voltage across the resistance. So yeah, this stuff doesn't work when you're close to stall. But if you're far enough away from stall, it does work pretty well.
Speaking of, here is the motor speed, torque, current, everything curve. There's a lot going on here. So yeah, essentially the x-axis is your torque and your y-axis is your motor speed. So as we were talking about before, if you increase your current, as you increase your torque, your current has to increase to support that. And as you conversely, the speed also drops until you reach stall. I'll go through sort of the way I've structured this is a bit different to how I'm doing it now. So I'll just go through how I planned. So yeah, you can see current is proportional to torque. And worth noting that heat generation is also proportional to current squared. So if there's too much torque on your motor, the current will be too high and the motor will overheat. So you've got to be careful about how much current is going through. The nominal torque, so this vertical black line here, is the amount of torque that the motor can drive continuously without overheating. And this is defined by the continuous current limit. So if your motor can only dissipate 100 like 10 amps worth of heat, then whatever torque it drives at 10 amps is the nominal torque. So with nominal torque, you get a corresponding nominal current. And I don't know what that other nominal was meant to refer to.
But emphasis on nominal for all this stuff, it's entirely a thermal limit and will be changed by its environment. So you might see a drone motor with some ridiculous current rating. That's because it assumes it's got a gigantic fan blowing directly over the coils. And conversely, if you take a motor and jam it in the motor tube where there's no airflow, suddenly its nominal current might be way too much. So that's a thermal limit, and will change depending on the environment. So you really do have to think about it as nominal, not like some hard and fast rule. The only way to really know is to test it.
Yep.
The other thing to note there is different expectations of lifespan for those motors comes into play here. An industrial motor is going to have a lot lower operating torque, simply because it needs to remain cool to prolong its lifespan, compared to like a hobby drone motor, which can overheat like mad because they just want to make another sale of the motor when it burns out eventually.
Yeah.
And the
Also,
hotter things get, the less efficient because the resistance rises. So in an industrial setting where they actually care about efficiency, you want to run things cool. Whereas in hobby brushless motors, a lot of the times they're rating this based on how hot it can get before you hit like the Curie temperature of the magnets, which will stop them from physically functioning, or it bursts into flames.
I'd add one
Also-
more thing as well.
Sorry.
So these motor torque curves, that's usually done at constant voltage.
Yes, sorry, yeah, this is at constant voltage. Yeah. So a motor will have what's called a nominal voltage, and that'll be what all of its stats are measured at, all of its specifications. So you'll see it might be like 6 volts or 24 volts. So those numbers won't apply at a different voltage to what is on the nominal voltage.
And I was just going to quickly add on the temperature limits. Generally around 100 degrees or so is where the insulation melts off the rotor windings on a brushed motor. At that point, you end up with a big resistor rather than a motor.
Yeah. Ouch. Yeah, that's never happened before. Okay, this is probably the easiest one. No load, zero torque. So right along the y-axis there, with no torque on the motor. So just spinning like you've just plugged it into a power splicing on a bench. This is the absolute fastest it can spin, and it will draw its quote no load current. So you can see that the current doesn't actually intersect with the origin. There's some minimum current required to get it to spin. And yeah, so it will drive at its no load speed with its no load current, and it will drive as fast as it can go. Stall is the opposite end. So stall, if the torque is so high that the motor stops spinning, this is stall essentially. And at stall, as we were saying before, it acts like a resistive load, and the current is really high. I think the 775 motors on the last year's suspension was something like 60 amps stall. So you really want to avoid this, because not only will you very quickly fry your motor, but you can also fry your electronics that drive your motor. So it can be quite dangerous.
It's also worth noting that stall torque actually limit is often extrapolated from data, because you can't get a proper measurement from a molten pile of slag.
That's true. The other note is that because the motor has stopped spinning, it's going to struggle even more to cool itself. So for example, the 775s have a little like propeller basically in the back that pushes air through them. That is no longer spinning, so they're not going to get any air to cool them down. And if it's not obvious by the curve, this is substantially higher than the continuous nominal current limit. So yeah, avoid this. Cool. Last thing on this curve, max power and max efficiency. Max power is probably the easiest. If you just multiply the blue curve by the red curve, you get this like inverted quadratic. That's your max power curve. And you typically want to design your things to operate around max power, kind of. But obviously this is higher than the continuous rating current. So you got to be, it's a bit of a catch-22. And I'll talk a little bit about this in the future. And then yeah, your max efficiency curve, we don't really care about this, but this is where that E term in the equation gets as close to as good as it can, whether it's as close to 1, basically. Yeah.
Yeah, typically about 0.8 or 0.9, depending how much you spent on your motor.
Yeah. Yeah. Cool. Any questions on all of what we just did?
So for this graph, the applied torque is like the cause of everything, right? So
yes.
the torque causes the motor speed to slow down, and that causes current to rise because back EMF is reduced.
So this graph does kind of seem to contradict what we were saying before about the torque proportional to current thing, but it's for a reason. It's because of that RI term in the differential equation, right? So at this, the supply voltage is being kept constant, and you're assuming like you're not expending any voltage to change the current. So the current's constant at any point in this graph. So the only two things affecting it are the back EMF and RI. So resistance times current. So as you increase your torque loading, that will increase the current. So it increases your current by 1 amp, but then that amp gets multiplied by the resistor and might drop the supply voltage 1 volt, which means you can't supply as much back EMF anymore, because now a volt of the power that was going into the back EMF is now being expended over the resistor. So it slows the motor down. And then you load it more, it increases the current more, your voltage drop across the resistance increases, which then decreases the amount of voltage that can be used to overcome back EMF, which drops the speed. So that's why that relationship is a straight line. That's actually just because of Ohm's law. But if you're changing the voltage, which is how you actually drive a motor, it looks very different.
Yeah, and I guess in short, you'll be operating up around here most of the time. So a lot of the details get a bit fuzzy.
And sorry, another question. Is the nominal current where that vertical line intersects with the red?
Yeah.
Yeah.
Yeah, cool. All right, questions for you. Haha. This is going to be a bit of a test. A motor is spinning, but at too low speed. How do I increase the speed? Come on.
Is the torque constant?
Sure. Yep.
I guess you would increase the voltage.
Yep. Exactly. All right. Harrison gets the easy one at the start.
Whoa!
A motor starts drawing more current. What has changed mechanically? So think back to the mechanical power equation.
More load.
Correct.
Torque
More
component.
torque on the motor. Yep. I decrease the voltage across the motor from 12 volts to 5 volts. What happens?
Slows down.
Yep. I set a 2 amp current limit on my power supply. What does this affect?
Torque.
The speed.
Yeah,
Depends.
so it's a bit complicated, but yeah, torque
like
is a simple answer. As you increase, it affects the maximum torque you can do. So yeah, basically it will hit stall faster because it can only get 2 amps, and then all the voltage will be dissipated across the resistive load, like Christos was saying, and it'll stop spinning. So yes, the speed will go down if you hit your current limit. I grip the wheel and the wheel slows down without changing voltage. Isn't speed proportional to voltage? What happened?
Well, you know, the current still goes up,
Yeah,
right?
yeah. So why did the current go up?
So you increase the load. It seems like this would be where it's acting quite resistively.
Exactly. Yeah. So this is actually one of the key points that's really confusing about motors is, I said, if you decrease the voltage, it'll slow down, but then I grip the wheel and it slowed down. Does that mean the voltage went down? No, the voltage supplied is the same, but the voltage in that EMF term is less because the IR term is higher, because we've got more torque applied. Hopefully that makes sense. And lastly, what happens if I run a motor above nominal current for 1 second versus 1 hour?
You go to jail.
It goes faster. 1 hour gets hot.
Yeah, so I'd say at 1 second, not much. It will be able to supply a bit more torque for that 1 second. But if you're running it above nominal current for an hour, at least a lot over nominal current, then continuously, it'll probably die. So because it'll overheat. And then, as Aidan said, the windings will melt and you'll get a nice pile of globs. All right.
Big old power resistor.
Exactly. Any questions on these questions before I move on? Anyone confused about one of them?
Wait, what's the point of the current limit? So it doesn't stop your motor dying. Yeah, you can still stall it and kill it, right?
Yeah. So like the 775s have a 60 amp stall current. So if you set a 2 amp current limit and then grip it and stop it from spinning, then you're just going to be sending 2 amps through it, which it can do pretty comfortably. Now it will probably overheat a little bit eventually because it's not spinning anymore, so it'll struggle to cool itself. But you're only putting 2 amps through it versus 60 amps. Yeah, does that make sense?
So you can stall it for a much longer time before it overheats.
Well, so
Just think about where the energy is going. So if it's not spinning, it's not outputting any mechanical power. All the electrical power going into it is essentially being converted to heat.
Yeah.
So if you have a current limit set at 2 amp, that multiplied by your voltage is the amount of heat generated in the motor. If you're sending 2 amp at, the same voltage at 60 amp, that's a lot more like heat energy being generated in the motor.
So if you have overheating issues, you just current limit it.
Yeah, or load it down less, or do something to, pull the motor back towards its normal range.
And if you set that 2 amp limit and you're at the 2 amp limit and it's stalled, does that mean that your supply voltage would have to decrease?
Yeah, well, your power supply would decrease its supply voltage in order to hit the current limit, in order to trigger the current limit. So it's sort of backwards.
Yes.
But for context, Taha, in the CMDs, we have a 10 amp fuse on the motors and probably like, I don't know, like 5 amp software current limit ish.
It's a 15 amp fuse and 10-ish, 10 to 12 amp software.
8 amp practically. Measure.
If you short it, it's 8 amp, but it'll hit peak currents of 12 amp before it will properly current limit. It's weird. It's not a current limit like the way a constant current power.
We get into this later, right?
Yeah.
In the CMD presentation, which is next week.
Oh, okay.
Actually, no, there's a thing with current chopping. Yeah.
I think there is in here. Yeah.
Anyway, I better keep moving, so I was going to be here for hours. Cool. A bit on speed control. If you haven't done control systems, you should still be able to understand this. But if you have, you'll have a much better understanding. So when the torque on a motor varies, how do you maintain a consistent speed? This is something that we do with the Rover wheels and the arm joints as well. So you can, as we talked about before, you can adjust the voltage on your motor to adjust the speed. We can do this using PWM. And so the way that it works on the CMDs is we get knowledge of the motor speed from the encoder that's coupled to the shaft on the motor. And then based on how close we are, so we use a PID controller, if you haven't done control systems, essentially based on how close we are to the speed we want to drive at. If we're under it, we increase the voltage. If we're over it, we decrease the voltage until we're driving at the velocity we want to. If you've done PID control, you know that's not exactly correct, but it's good enough. Yeah, so that's how that loop works. And you can see this disturbance or load step. So that's the input of like external torques. So you start driving up a hill or someone grips the wheel and it tries to keep driving at the same speed. Cool. And this is like what we were saying before, when you grip the wheel, the speed goes down, right? So in order to, when we grip the wheel, keep the speed flat, we increase the current. Sorry, we increase the voltage, which also increases the current. All right. Any questions? All good. Cool. This is a bit on current chopping. Basically, in the CMDs, if I actually mainly put this in because it shows you what the current does in a motor at a very zoomed in level. You can see it wiggles up and down. This is an extreme example. Ideally, you'd have it only sawtooth a little bit. But basically, if in the CMDs, if the current so in this PWM cycle, right, if the current reaches a certain threshold, the rest of that PWM cycle will be turned off, and then it'll try again at the next one. There'll be more detail on this in the CMD presentation, but this is another prevention against really high stall currents, because if you start drawing, if this blue line starts to increase up to that 59 amps, it's very quickly going to hit that threshold and it's just going to turn off the rest of that cycle. All right, over to Aiden.
Cool. I was just about to type, I was halfway through typing an answer to Alex's question in the chat there. But setting a current limit on a motor, that graph would basically just cut off at that current limit because current's proportional to your to output torque. So it would just like end. However, at that point, you have kind of stallish conditions where like the motor stops spinning and it kind of weird things happen. So at that limit, you'll end up with like a drop off in torque as well. But yeah, cool. I'm going to quickly walk through a couple of ways to select motors, ways that we've done in the past, including dodgy methods listed here. So we've got like decent motor configuration utilities, which are like Maxon is the main one we've gone through, as well as Vex Pro for chassis. There's a few other configurators out there as well, but in general, good motor configurators for brushed motors are kind of rare. There's not a whole lot of applications for really high power, high performance brushed motors these days. Most people just go straight to brushless. A configurator, we're going to walk through the configurator of Maxon just as an example, but it's basically where you can pick your motor, you can pick your gearbox, and you can pick any accessories like encoders or shaft types or all sorts of things. And additionally, there is two separate ways to actually select these. In general, a configurator will get you to choose the actual power of your motor, whereas a torque-based approach is often like a trial and error sort of thing that you might attempt if you just like find a motor on AliExpress and just want to see if it'll work for your application. It's a lot less specialized. In general, we want to almost always choose a power-based approach here, as it takes into account both torque as well as speed, and allows you to more optimally find a motor that's going to suit your purposes and keep the weight down. Next slide, please. Yeah, Seaman, if he's still here. So first of all, we're going to go through the power-based ones. This is going to be pretty much every configurator that you'll be doing. If you're able to select a particular motor, you're able to select the kind of power band where like the nominal torque on that torque versus the torque curves we looked at earlier, you can kind of pick exactly where that nominal power band is and direct it towards like where your torque limit is. So this is pretty good because you just have to select through a range of different motors and pick one that's closest to what you need. So power is simply a property of the motor, not the gearbox. So let's say the 775s, the motors, that can be typically rated about 50 to 100 watts. It does vary per model exactly, but we just slap on a gearbox on the end to actually output the required amounts of torque or RPM.
Are we referring to output power of the motor or input power?
Output power. Pretty much throughout this whole thing, I'm just going to talk about output power. Often when it's very often it'll just be the output power. Often when you're operating at the at the nominal range, it'll be close to like 80–90% efficiency. And at that point, it's actually not a whole lot of difference there. You generally pick a power that's above the level that you need. In this example, we're going to select a 40-watt motor. If in your torque calculations, where you take your torque, which is Newton meters, multiplied by your required like rotational speed in rads per second, you'll end up, say you do that calculation, you come up with like 30 watts of power needed, mechanical power to actually drive this. In that situation, a 40-watt motor like this will electrically as well as physically be able to power that motor, power that application. Does that make sense?
Yeah, that makes sense.
Yeah. All of these figures are going to be sort of like approximate. You generally want to overspec everything you do. And in general, you don't have a choice not to do so because there's 40-watt motors or there's like 20-watt motors. And if you need 30 watts, too bad. You just got to go higher. Don't pick one that's underneath the power limit that you require. So I've done a full write-up on the actual selection process on Euclino if you want to follow through like step-by-step in your own web browser. But I've got a few snippets of the actual Maxon motor configurator here. So first thing you do, and literally the only thing you really need to do here is select the power parameter, and that will let you select a different one of a different range of Maxon motors that can deliver that power band. In this case, the parameter on the left image there is simply power set to 40 watts. A graph will load down the bottom, or a table loads down the bottom, displaying every single motor that can provide that much power. You can see the DCX26L is the model that we can select here. After clicking on that one, we can proceed on to configuring the motor for a gearbox attachment. So next slide.
Question from Alex: is the rated current synonymous with max stall current or nominal current?
Are you talking about?
Sorry, I mean power.
Maximum power.
Yeah.
Oh, sorry.
Maximum power is very different to stall current. So that's like roughly 50% along its torque curve. If you remember that yellow line, there's like a big arch. Yeah. That's like middle, about 50%. Very often a nominal, it will be less than 50%, generally around 25% to 30% of the maximum of the stall current. It does vary a lot. Again, this is a thermal sort of consideration. If you have a really, really well heat-sinked motor, you can pull as much heat out of the motor as you can. You can operate closer and closer to the maximum power limit, the maximum power point in your torque curve. Does that make sense?
The question was, what does the rated power refer to on the slide?
Nominal power.
So the power at the nominal torque, right?
Yeah.
Okay.
Yeah. So nominal is just a vertical line on that torque graph, and each one of those things. So nominal efficiency, nominal torque, nominal current, nominal power. Simply like that is a state of the motor. That vertical line represents a single state, a single load case of the motor.
Yeah. Thanks.
So the motor can theoretically output a higher power, but that will be beyond the nominal range, so it will just likely burn out the motor.
Depends on the time period.
Right.
So in this case, a Maxon gear motor is able to output a fairly high amount of power for a reasonable amount of time, owing to the high efficiency as well as a fair bit of thermal inertia. So you can run them at, close to maximum power, maybe for, I'm going to say 10 seconds or so, without any serious implications. Whereas an air-cooled motor, you might burn out at such a situation. Okay, cool. Does that answer everyone's questions? Neat. All right. Next up, we're up to the gearbox selection. So simply the next slide. All you got to do here is basically figure out how much torque you need and slap on a gearbox that's able to reduce the output speed of the motor down to a usable amount. Keep in mind, all this is doing is to our mechanical output power from motor is transforming it into a slower RPM and a higher torque. This means that we don't have to output as much torque directly from the motor, and we can basically shift our line of, actually, that's not a good way to describe it. We're essentially not slowing our motor down nearly as much as a proportion of its output power. So this allows us to not stall the motor out as much. In this case, if we know the amount of torque we need, let's say it's 2 to 3 Newton meters, or 2 Newton meters, we can input it on the preferences in the configurator. And again, they're just a bunch of bands. You can pick a bunch of different types of configurations that will achieve a similar amount of torque. And yeah, once you've selected it, we find that a GPX26 two-stage at, which one did I select? Doesn't really matter, but any of those gearbox configurations will output healthily that amount of torque. It's important to note other considerations for your gearbox. So backdriveability, if you need to have it so it only will drive forwards, not forwards, but it can't backdrive. So any load on the output does not rotate the motor. However, the motor can rotate either forwards or backwards, and it will move the output shaft. In general, Maxon doesn't do worm gear motors, worm gearboxes, but a lot of other configurators might do so. Other things would be drive shaft type. If you want a hex shaft or a D shaft or keyed shaft, these are all options. I don't think the Maxon motor offers it for all gearboxes. You'll have to pick one of the large gearboxes to get a keyed shaft or something similar. So this is what I'm about to get to. Thank you for asking. So small gearboxes such as this particular one are not limited necessarily by the amount of reduction they have in them. So let's just say you have like the tiniest of motors and you gear it down like 1 billion to 1. The output torque of that gearbox is going to be limited not by the amount of power that the motor can deliver, but by the individual teeth in that last stage being able to transfer that torque. If you ask too much torque from a gearbox like this, those are just going to snap in half, and you'll end up bending gear teeth, shredding them off their gear hub, and yeah, you'll end up with circles instead of gears. So that's generally the limit on these. This will be a mechanical limit for this particular gearbox, and they'll ask you not to exceed that. For these sort of motors, because it's such a relatively small motor, it'll end up just backdriving the motor and doing some weird things, but that's what Maxon suggests. It doesn't expect anyone to put such a motor in a situation where it's going to exceed this amount of torque. So that's why they're limited to that. M is, yeah, maximum torque. They don't even say that like anywhere. You just have to kind of guess at it. But yeah, that's maximum torque. That is maximum rated torque. So that vertical line on your graph. Cool. Any questions on gearboxes? Ratios of reduction in speed. Yes. So if you've got a 16:1 ratio, you'll be reducing your speed by 16 times. Keep in mind, there's also an efficiency term on each stage in a gearbox. So this is a 2-stage gearbox. If each stage is 90% efficient, then the output is going to be 81% efficient. That works, right? Yeah. Anyway.
No, I was going to say, I noticed there's no like figure for backlash in any of these selections. Is that something that comes into consideration when you're selecting a gearbox?
Yep, that'll be a other requirement essentially. If you need really low backlash on something, then you need to look into specialist gearboxes. Maxon delivers really, really high performance planetary gear motors, but they are not spec specifically for backlash reduction. If you're looking for something like that, you need to look into specialist ones such as cycloidal or harmonic gearboxes. In general, you don't use planetary for massive reductions in backlash, simply because they can backdrive. And yeah. Any other questions I've missed in the chat? No. Okay, great. Okay, next slide, please. Thank you. So torque-based, this is kind of a dodgy approach. How much time have I eaten up? Sorry.
Yeah, that's all right. We'll go over. Sorry, guys.
I'll try to get through this pretty quick, but this is essentially the way that we've done a lot of our motor selection in the past. This is where you just find motors online and you just compare it to your selections. And if it doesn't meet the right amount of torque, then you discard it. So this is the primary way to choose pre-configured motors from resellers. By resellers, I mean companies that do not make the motor, hence they can't configure the gearbox and motor combination for you. They just buy them in bulk off of their supplier and they resell them in the configurations that they have. This is bad because it doesn't consider, very often you have to pick it based on torque. So if it outputs enough torque, you just pick that motor and you just deal with whatever RPM you get at the output. Very often this is like not a great way of doing it because you'll end up with a motor that is either too small to do the job and you'll end up with driving it very, very slowly, or you'll end up with a motor that's way too big and heavy for what you actually need. This is why it's not a great way of doing things, but it's by far the way that we choose motors the most. So yeah. So it's good for if you don't care how fast it goes, if you just need to like move something out of the way and let's say you don't have a lot of load on it. So if your torque is very, very small, you can get almost constant torque, constant speed out of a gearbox using this sort of method. But in general, we want to attempt to find some way of figuring out what that output power is. Any questions on those points? Cool. Next slide. And I've got a quick example here from Core Electronics, basically looking for a motor that can deliver and a reasonable amount of torque. If we just pick like a random gear motor off the shelf, we can see that this one is 25 millimeters in diameter, so it's sort of similar to the Maxwell motor. However, if we look at the torque limit, it says about 3.9 kilogram centimeters, so 0.1 Newton meters. You can look at the rotational speed there as well. Where is that? It'll list it on a different category basically, but that's essentially the maximum amount of torque you can deliver continuously. So we take the stall torque, we divide it by half. That's about the maximum power you can get out of the motor, about 0.2 Newton meters. However, that is only in short term. So similar to what we said before, for a second or two, it might be okay. But given it's an air-cooled motor, we want to run it considerably less than that. Generally, about 25% of stall torque continuously is okay. For cheap motors like this, you might want to derate it even further. Yeah. Any questions?
Cool.
Okay, get back to it.
All right, brushless time. Hopefully this makes sense. I think it will. All right, so if we think back to like the first slide and we had our magnets on the stator and our coils on the rotor. Now it's the opposite. So this diagram here, the coils are on the stator. Stator doesn't move. It's stationary. Stator, stationary. And the rotor has the magnets and the rotor rotates. Rotor rotates. That's how you remember it. Stator, stationary. So yeah, now we no longer have a commutator. We no longer have brushes, and we now have magic. And that's how we get it to spin. And that's not that far from the truth in a lot of ways. So if you think back to the animations at the start, the way that we got the current to change direction through the coils when it completed a 180-degree revolution was with the commutator. But there is no commutator anymore. So how do we get that current to change as it rotates? And the answer is we do it ourselves, or the motor controller does it. So how do we know when to do that is the question. And there's many answers to that question. Before we get to that, typically, so this represents, so you can see if the dot is blue, it's a north pole, red is a south pole, or the opposite, it doesn't really matter. And white is like nothing, just disconnected. So we have the rotor with the magnets is in the middle with the pink lines, and the coils are on the outside. And so those magnetic fields on the outside are induced by the coils, and the magnet inside is spinning. Now, you'll see, so typically, so for example, the motors that we're looking at for this brushless arm concept have 7 pairs of magnets. and I think a few more, yeah, and some amount of coils as well.
E4, I believe.
Yeah, and so, and here we have a one pole magnet, a one pole pair, two pole pair, and four pole pair. And so it's essentially you can increase the number of coils, increase the number of magnets, but the operating principle is the same. So we're going to use the one pole pair as standard for explanation because that makes things a lot simpler to understand. But you just need to increase if you double the number of magnets, you just have to switch your coils twice as much as you rotate, basically. Any confusion so far? Cool. All right. So yes, magnets. So basically we've got our three coils up in the top right, and we can send the current through those in two different directions each. So each coil can be a north or a south. And you can see as this GIF progresses, the colors will switch. So this is red, blue now, and then when it turns off and back on again, it'll be blue, red. And what that means is you can get 6 different magnetic field orientations induced by the coils. So that's a lot of words. So for example, if you have so each of your 3 coils, you can have one pulling. So for example, here, if we turn the A1 on, then we get this red magnetic field pulling this way. And if we turn the blue one on, blue is a negative magnetic field, so it's going the opposite direction. We add those up and we get this green magnetic field sort of pointing to the top right. And if we repeat that process for all of them, we get an arrow up here, arrow vertical, arrow up to the left, arrow down to the left, arrow vertical down, arrow down to the right. And you get these 6 green vectors here. So the 6 possible magnetic fields that we can generate in the brushless motor. And the rotor will essentially chase this magnetic field. So the blue end will try and reach the green arrow. It is how it works. Ideally, we want the magnetic field vector perpendicular to the rotor because that gives us the most amount of torque. So in all of these cases, the rotor is basically in line with the magnetic field vector, which doesn't induce any torque. But you can picture that, if you held the current in with that one position, the rotor would rotate to that one spot and then stop. And that's actually quite bad if it stops, because that means your coil is now a resistive load and you're at stall, or you'll get stall current across the coil. So yeah, and because we only have 6 possible states of the magnetic field vector, we will have up to 30 degrees off from our rotor from nominal torque as we switch. You can never get perfect torque all the time with this, as you can't with a brush motor.
Could we get additional states by having 2 coils in the same direction? Like that 30-degree alignment, if we made both A and C red, we would get another state, between the 330 degrees and the 270 degrees.
Yes, so you could, if you actually do the maths, that vector would be like out here, right?
Yeah.
Which is the same as this, but weaker. Or it's not the same, but it's close to. But it's not as strong. The real answer is that these are in a delta configuration. So to have current go in, you have to have current come out of another.
Okay.
And so you always have to have 2 the opposite. I swear I had a slide on this, but maybe I got rid of it. Or maybe it's only, yeah. So that's annoying. I wish I did that. Anyway, there's details on the neutrino. I must have forgotten this one bit. But yeah, so it's actually wired up how it is here. So you've got the 3 wires coming out, and the current comes into this one, and then through the outer ring here, and then out.
Oh, yes.
Yeah. Cool. So it doesn't really look like a delta, but it is a delta. Sorry, it's not a delta. It's a what's the other one?
It's a Y.
A Y. Yeah, thank you.
Oh, sorry, but is the operating principle of this, like, I mean, so for brushless DC motors, the direction of the current is controlled by a driver, right? But isn't this like the same concept as like a 3-phase AC motor? essentially.
Exactly, correct. It is a three-phase AC motor,
Right.
basically.
Except like with three-phase, you don't really need like a controller, do you? Because it's just like the fact that the three phases around like
So if you want to change the speed of a three-phase motor, you need
like
you
a
need to
variable frequency
change
driver or
the
something.
frequency of the oscillations. Yeah. Now the question is, so we know that we need to set the coils to each position to get the rotor to attract to the right spot. But how do we know where the rotor is? It's not like a brushless motor where if you just apply voltage, it's going to spin. If you just apply voltage, it'll rotate a little bit and then stop and do nothing. Aidan, I think the answer to that question is that all stepper motors have inbuilt current limits.
Yeah, so just more resisty wire, basically.
Yeah, well, and just like the stepper motor drivers will not drive above a certain current. It's very low.
Almost all stepper motor drivers are current controlled. That's why you like change that little knob on the crappy ones to set current limits.
Yeah.
They almost always run on voltages well under like what you're actually supplying them. Like the coil voltage for most steppers is like 2 to 3 volts. So you'll end up using constant current drives to drive them.
Yeah. Okay, so where is the rotor? We'll come back to where is the rotor in a minute. Just this briefly is the sort of operating principle on how you actually drive them. So on I realized I didn't actually put a slide in how an H bridge works, but you have 6 MOSFETs. If you want to put current through, say, this coil in the other direction, you turn this MOSFET on and you turn this MOSFET on, and the current will flow through. Now, if you want to halve the effective voltage across the coils, then you can PWM the MOSFETs and reduce it that way. And this is basically what this is. So you have your 3-phase inverter, which is this MOSFET, so this triple half bridge, basically. And you have your PWM driver that sends the pulses to the 3-phase inverter. Alex asks, this seems identical to 3-phase AC generator, as Harrison said. Why is it called brushless DC? Yeah, they're also called permanent magnet synchronous motors. The answer is basically that they run off a DC supply and not an AC supply, in short. It's more about you could in principle hook one of these up to like a mains voltage if it was rated to that voltage, and it would try and spin at the right speed. But
the other main difference between like a 3-phase generator, an asynchronous motor, is that they don't actually have fixed magnets. Quite often they'll just run the AC through like other coils on the outside. It's actually cheaper to do that than actually buying
what
like
you
massive
normally hear
fixed
of
motors,
as a
magnets.
As a 3-phase motor is a 3-phase induction motor. So there's no magnets, it uses induction coils. A fancier name for BLDC is permanent magnet synchronous motor. So they are synchronous motors, just like an induction 3-phase motor, but they use permanent magnets. Technically, there is a distinction between BLDC, which has a trapezoidal back EMF, and permanent magnet synchronous motor, which has a sinusoidal back EMF. But in practice, no one actually pays attention to that, and they'll use whatever name they want.
The practical difference is largely the control side of things. In a asynchronous motor or induction motor, AC induction motor, you are just given your frequency from the grid. You can't change it. Whereas a BLDC, you are in full control of that, and you can optimize the motor power based on its RPM or location of the rotor.
The other thing as well I'll mention is that we will later develop it to do it this way, but at the moment we're not actually using sinusoids to drive the motor. At the moment we're just sending it square waves basically through each coil, essentially. So that will come later, but yeah. Any questions?
What does synchronous and asynchronous refer to with the motor?
The RPM will be exactly what the input frequency is for a synchronous motor. So if you want to spin it faster, giving it more voltage doesn't do anything. You have to increase the frequency.
So an AC 3-phase motor, can you just not change the speed at which that operates?
Correct.
Yes.
And in general, the rotor will actually lag behind the driving frequency.
Do they? Yeah, I don't know how they use AC motors in practice. I presume they have like a variable.
Not normally, only where you need them. Normally, they are given a fixed load, and they will always run at that speed.
Yeah, right.
Like continuously for their
Have you ever
entire
used
lifetime.
the drill press? Have you noticed that I have a bunch of like belts on it, and you don't actually control the speed? You have to gear it down. That's because they can't actually change the speed of the motor. Or like a mill has that continuously variable transmission to change the speed. It's because
They're designed to be as dumb as possible.
Yeah.
All right, let's keep moving. So back to where's the rotor? Part one. This is I think it's a 4-part series on where's the rotor. We don't know, so let's just try and drive it anyway. You can do this. It's not very good. You can run a brushless motor with absolutely no clue where the rotor is. You essentially just cycle through those 6 magnetic field states at a frequency that is probably about right, and hope that the rotor's following along. It doesn't work at high speeds. It doesn't work at very low speeds. And yeah, it'll jump if you do it wrong. Like if you do it too slow, it'll just jump between the 6 positions and dump a lot of current. And it's also really inefficient, but it does technically work. So this is a good place to start. So you can see
similar to how. Sorry, is that similar to how a stepper motor works? You just put the field, it goes to that position, and then you make the field slightly different. It goes to that.
Much faster. So if you tried to operate a brushless motor as a stepper motor, it would dump a lot of current because they're not, unless you have really good current control, which you probably don't because you're running it like this. This is more just an illustrative first step. You wouldn't really ever do this in principle. But you would speed it up so that it actually works. If you watch the Great Scott videos that are in the Neutrino article, he does this as the first thing he tries. But you can see the currents through each of the 3 coils, below the line if it's negative, above the line if it's positive. And the winding currents are not sinusoidal, so they're square waves. It's either negative, positive, or 0. Sorry, I just got like a random spam call. One random note, you'll see this everywhere. UVW, that refers to the 3 coils. So you'll see, well, like the 3 coils basically. Any questions on this? Cool. Part 2.1, we're going to guess where the rotor is. So this is our old friend back EMF. So okay, I didn't do as much on this as I wanted to. Hang on a sec. I swear I wrote more about back EMF. I must have like deleted the slides back, so hang on 2 minutes. Let me just pull up the Neutrino article. Because I wrote more here and it will actually explain it properly. Okay, so yeah, this is called sensorless or back EMF. So basically, when you have, so you've got this like resistive part and some other, this is actually not as good as I remember. I swear I wrote something good about this. Anyway, I'll try and explain it with words on those slides. So say you've got, the easiest way to picture it is say you've got your 2 coils that are magnetized and your 1 coil that isn't magnetized and it's just sitting there. As that rotates through the other magnets, well, actually, as the rotor rotates past it, that's going to induce a voltage on that coil because of Lenz's law. So the flux through that coil is going to increase, which will induce the voltage on that coil. Are people following along? Does that make sense? I'm not getting any nods.
Can you say that again? Sorry.
Yep. So you've got your 2 coils that are magnetized and the 1 coil that's not. And as your rotor rotates past that coil, so the rotor has the magnets on it. As that magnet passes the coil, it's going to induce a voltage in that coil because of Faraday's law.
So that Faraday's law states what? A change in magnetic.
A change in magnetic flux is a change in voltage.
Okay, that makes sense.
It induces a voltage. Cool. So
not a change in voltage though. A change in flux is a
yeah,
constant voltage.
Induces a voltage. Yeah.
In the in the coil that is not magnetized, right?
Yeah, so that's a simplification. That's a simplification to understand it. In principle, we will be magnetizing all three coils later on.
Right. Yeah.
But you still can calculate the back EMF by measuring the current through the coil, through each individual coil, and multiplying by the resistance of the coil, and that'll give you the IR term, and then your input voltage will be bigger than that, and whatever the difference is, that's your back EMF. Does that make sense? So you can measure it on a magnetized coil. Anyway, easiest to picture it as just working on the disconnected coil, but you can do it with the connected coils as well. Anyway, the important thing is that when the back EMF crosses 0 point of the, so yeah, when basically you get these graphs of the back EMF for all three coils. When it crosses the 0 point, that's when you switch to the next state of your 6. So it'll either cross up or down, and each of the three coils will do it. So you get 6 different transitions, and you basically just just measure this voltage, and then have a lookup table to know which state to transition into next, and then change the currents on your coils. Does that make sense? Probably not. Probably not super good. Any questions or any sticking points where you got lost?
So when the back EMF through one of the coils is 0,
yeah,
at that instant the rotor is the magnetic moment of the rotor is parallel to the plane of the coil.
Yes.
That's when the change in flux through the coil is 0.
So basically the magnet is next to the coil, pretty much.
Yeah.
Yep. And then that's when you switch to the next state. So you magnetize that coil that it's next to, and it'll start pushing it away, and it'll have a bit of momentum, and it'll keep pushing it, and you magnetize the one that's next to pull it towards that one. Yeah. Other questions? I know I didn't explain that very well, so there must be more. Does anyone want me to explain it again?
I think the diagram's pretty good. It's just like you've hit peak north or peak south, and it's in front of the doodad, and then it switches.
Yeah. Taha,
can we measure it? Can we measure that voltage in a coil that's already energized, or is it simply one that is not energized?
Yeah. So let me show you. So using essentially this, so we lump together the voltage source and the inductive term into one. You measure the current into that coil and the voltage you're supplying, and take the difference, and that gives you something proportional to the back EMF, basically.
Disgusting. Okay, cool.
Yeah, it's gross. It's very hard. Taha?
So when you change the torque, it's gonna adjust the way it powers magnets. If you suddenly hold it, so it's gonna notice that it's spinning slower, and then it's gonna adjust it, right?
Yes.
So
yeah. So it'll if you increase the load, it'll start spinning slower because of all the unintuitive stuff we talked about before. And then because it's slower, the back EMF will cross less often, so it will switch states slower.
Yeah, makes
so
sense.
It won't get lost. Cool. One thing to note, so you've got this derivative, right? So it's proportional. So the back EMF is proportional to the derivative of the flux. So if your motor's moving really slowly, your back EMF is not going to be very big, and is therefore going to be really hard to detect. So this only works at very high speeds. I remember. It's part 2.2. Here we go. We're going to get better. Hey, I remember now. Okay, here's what I was talking about. So we know the voltage of the connected coils, the resistance of the coils, and we can measure the current through the coils. And then so we can calculate epsilon, the back EMF. There. So that's what I was just trying to explain with words, but better. Like I was saying, it works very high for high RPM motors like drone motors, but doesn't work at low RPMs because the delta T gets very big, and therefore your back EMF gets very small. Cool. All right. I'm glad I figured out where I'd put this information. Any questions now? Hopefully that clarifies things.
So does this mean any low RPM like brushless motors you get are actually just a really high gear ratio gearbox attached to a high RPM motor?
If they're senseless, yeah. Well, yeah. So this is very basic. This is like dumb how to control a brushless motor. It's one better than guessing where the rotor is because you actually have some idea, but it only works at high speeds because of the back EMF generation.
Basically, if you know you need to be able to get torque out of your motor at low speeds, you don't use this method. It works great for drones because if your propeller is not spinning fast, you're going to be falling out of the sky anyway. But it's really not good for what we want to do. So you wouldn't use it for a rover. For the arm or for the wheels, for example, we want to be able to drive at very low speeds. So this just won't work, full stop. Or like hold it at a 0 speed is a thing you can do. It won't work because there's no back EMF to detect because it's not moving. In fact, to get the motor spinning like this, think about it. When you first start the motor up, you have no idea where it is. So you have to start by blindly spinning it for a little bit and then hope you pick up some EMF. Yeah. Cool. All right. Next bit. This is exactly the same. So you still have the 6 commutation states. But now we're using Hall effect sensors. So the great thing about brushless motors is you've got this big spinning thing with magnets in it, and Hall effect sensors are very good at detecting magnets. So you have 3 Hall effect sensors in there, and as the rotor passes, they're not on this diagram, but you can see them embedded in here. As the rotor passes them, you get this output square wave signal. It's basically a quadrature signal for your magnet position, for your rotor position. And so you can decode this to get, so there's like literally there's 1 electrical cycle here, there's the 6 states contained in here. And based on that, you can decode which 1/6 of a rotation the motor is in. And like I mentioned before, it's a 1/6 of like a electrical rotation or a magnetic rotation. It's not necessarily a 1/6 of a full rotation of the motor. Because we're sensing the actual magnets, and there could be like 7 magnets on your rotor. Drew?
Yeah, so sorry. So these 3 motors in this, not motors, these 3 Hall effect sensors in this picture with the arrows, that's then obviously not spaced 120 degrees apart in phase. Exactly. Yep. So would you have to have a ring of Hall effect sensors going all the way around the motor to get each of those magnetic cycles?
So you need 3. Now, if your magnets if you only have 2 magnets, like a north and a south on your rotor, then you need to have them 120 degrees apart. But because whatever this motor is has probably like 20 magnets on the rotor, they're much closer together because you can detect, like, one of them will be in front of the north, one of them will be in front of the south, and one of them will be like not in front or in between 2 of them, basically.
Oh, yeah.
Yeah. Thanks. Or, well, yeah, it'll actually, yeah, good enough. Alex, you had a question?
Yeah, so can we hack this 1/6 resolution by having more coils? So if we had 6 coils, each with a Hall effect sensor, would we then be able to have, let me think, like, like 18?
Well, yeah, I see what you're trying to say. In principle, probably, but there's better ways to do it, which you'll find out in a minute.
But that is kind of what most motors do by having not just 1 magnet and 3 poles. It'll actually have like 24 coils. It's because if you're doing trapezoidal control, you'll get a ripple as it goes between each of the coils. So like you can see on that graph, if there were only 3 cycles or 6 cycles in each, you'd get 6 bumps throughout the rotation, and the bumps would be a lot bigger. But if you have way more coils than that, then you might get 24 bumps per full rotation. So your torque ripple suddenly becomes a lot less. So adding more poles reduces, it's called cogging torque. It's the amount the torque changes between each pole. So yeah, that is a way to do it actually, but you can still do it with just 3 sensors because you just have the 3 phases. It's just you've got like them mechanically closer together in the stator.
Aiden asks, why 3 sensors? Don't we use 2 sensors to find velocity and direction on an encoder? Yes, that is true. But we needed a position, and you can't encode 6 states with only 2 sensors. You need 3, basically. Just binary.
Well, you actually could use 2 sensors, but you wouldn't know. You couldn't use 2 digital sensors to get it because you've got the 6 states.
Yeah. So yeah, important to note that these Hall effects are either on or off. They're like Schmidt triggered. They're not analog.
But if we know how far ahead that like square wave is leading the as it's approaching each of the stators, wouldn't we know exactly where the magnet was actually turning on, like where the magnet was located?
What if it changes direction halfway between a cycle?
You still look at the pulse timing between the 2 overlaps, right?
No,
like if you just take channels A and B.
No, you don't use the timing at all.
Okay.
You literally encode the position. Like so this is 001 in the 3 sensors, which means it's in the first 30 degree 60 degrees of the motor or the electrical cycle, and then it moves to the next one 000, and then it's in the second sector. Yeah, so you always know where it is. You have an absolute position on the rotor. It's just really shit resolution.
So it's literally like a lookup table, like
exactly.
3 bits corresponds to.
Yeah. Cool. All right. So yeah, this is trapezoidal commutation. So it's easy to implement. You have the 6 states. It's called trapezoidal because you basically the shape of the back EMF. It's a bit weird. It's very easy to implement. You can do it with very basic sensors, 3 Hall effect sensors, or none at all if you can measure the back EMF and you're at high speeds. But because you can only be in the 6 states, you end up with this torque ripple because you know at any time you could be up to 30 degrees away from being 90 degrees magnetic field with your torque. So you get this torque ripple. It also doesn't work extremely well at low speeds. It does work technically, but you end up with basically a stepper motor moving between 2 positions. Cool. Time for the next step. So this is sinusoidal commutation. So Alex, this is kind of what you were talking about. So what our goal here is to always have the rotor, the magnetic field induced by the coils be 90 degrees to the rotor to get our maximum torque. So we want to eliminate that torque ripple by having it always 90 degrees. And the way this works is instead of only sending current like all our current through into one coil and out of the other coil, we can send some current through one coil and then we can split the current through the other 2 coils, right? And that means we can generate an arbitrary magnetic field in any direction we want. So we've got this circle of vectors. But that means we need to have independent current control through each of the 3 coils. Technically,
could you also do that with just 2 coils in like orthogonal directions?
No, because all the current going in has to come out of another one.
Yes, you can do it with 2 coils.
Oh, sorry, orthogonal coils. Yep. Yeah.
In fact, that'll come into play very shortly.
Yeah, true. Yeah. So yeah, we set up a current control loop on each of the coils. It's technically only on 2 of the coils because the remaining coil will just be the sum of the currents for the other 2. and we use PID control to control the sinusoid. So as it rotates, we want to increase the current, decrease, and make the current go negative and increase again through each of the coils as it spins to get it to spin around. Again, we haven't talked about how we know where the rotor is yet. We'll come to that in a minute. Now this works, but it doesn't work at very high speeds. And the reason for that is a bit of a technical control systems reason, but we're trying to control the current in a sinusoidal behavior. Now, if anyone's done control systems, you know that you don't use control systems to control sinusoidal things, to make things move sinusoidal. You make control systems move flat things, of slowly varying things. So as you increase the frequency of the motor, as it spins faster, this sinusoidal thing turns to really, really fast. And then you have to have a PID control loop that can track this sinusoid as it goes up and down, which isn't what they're meant to do, really. So yeah, a PID control loop is meant to get rid of oscillation, not track it. So it doesn't work at high speeds, in short. As I was saying before, ideally the magnetic field vector purple is perpendicular to the rotor in gray. So we've got this purple vector that's generated by the coils. It's the sum of the yellow direction, and there's this blue direction that's in line with the rotor, and this yellow direction that's perpendicular. Ideally, we'd want this blue vector to be 0, and it would all be perpendicular, and then we would get ideal torque out of the motor. All right, anyone got any questions on sinusoidal commutation or the ideal torque stuff? Because it's quite important before we move on. I know it's getting late as well. Okay, cool. That seems to make sense. So this is the last really hard concept. This slide looks super daunting, I know, but I'll try to explain it in a way that makes sense. First off, this is there are 3 different reference frames you can look at for your current. The first is what we've been looking at on the previous slides, so the ABC frame. This is just the current through each coil. So as current through one increases, they all sort of oscillate in this like helix sine wave as you do a full revolution. This GIF is very short, and I don't know why. But essentially, you've got this. You can see this cyan vector that's rotating, and all 3 of these vectors add up to make that blue vector. So all we're doing is making the cyan vector rotate around the circle. Now, if you're thinking for a bit, you'd be like, why are we using 3 axes in 2D to represent this one vector? That's a very good question. So what we can do instead is use what's called alpha beta frame. And we just use the XY axes. So this cyan vector is still here, but we sort of abstracted away by 1 step. So we're no longer looking at the current through the coils. We're looking at like this 2-axis current, which is like what Jory was saying before. And so you increase. So yeah, you just have 2 sinusoids. I'm sorry this isn't a GIF. I tried to get it as a GIF, but I couldn't find it. But you end up with a sine and a cosine, exactly. So they're 90 degrees out of phase. And so this transformation between the ABC and the alpha beta is called a Clark transform. And it's very easy. It's just like a matrix. It's got like some 1/√2s and stuff in it or something. Maybe over √3s, I'm not sure. Yeah, it's not that complicated. Now this last one is a bit weird. This is called the Direct-Quadrature frame. Now you're probably looking at this going, what the hell is going on? This is a reference frame that is moving with the rotor. So the axes here are moving with the rotor. So you've got this D axis, the D stands for direct, in line with the axis with the rotor. And the Q axis, which is perpendicular. So I guess technically not in line with the rotor, but in line with the magnetic field of the rotor. And so to do this, you need to know where the rotor is exactly. You need to know, like, to the degree or lower where the rotor is. And so to do that, you need some sort of absolute position sensing on your rotor. So if you're listening to our electrical meeting yesterday, you probably were kind of following along as to why we wanted this. And what this lets you do is you can see now there's this there's the current in the direct direction, and there's the current in the quadrature direction, and they're both steady state values. They're not changing, at least they're not changing nearly as much as the ABC currents are, which means you can PID control them. Right, so that's why you do it. That was probably a few steps to get there. But
I'd just like to point out the Park transform, you've probably used it before. If you've ever had to just rotate a reference frame, it's literally just rotating a vector in an arbitrary reference frame by an angle. You've probably used the formulas for that without realizing it.
Like the 2D rotation matrix.
Yeah, it's literally just a rotation matrix.
Any questions, Matt? You unmuted for a second.
I was going to say, is this the direct quadrature transform? This, and when you use PID control, that's field oriented control, right?
Yes, we're almost there. Yeah.
Cool.
No, if you're answering, Matt, go ahead.
No,
that was
all I said.
That was all.
Okay. So here, to get maximum torque, would we want the direct component to be 0 and the quadrature to be all of the rotor field?
Exactly.
Sorry, stator field.
So we'll get there in a second. But if you look at the diagram here, you might notice, you might figure it out. But yeah, so we use an encoder to get the position of the rotor, and we use current sensing to measure the current through each coil. And we do this transformation, and then if, as Dory said, if we minimize the direct current, so the blue term, and we maximize the quadrature current, the red term, then we will get optimal torque. So so the way this works, so we've got our 3-phase inverter, and we're measuring all the currents from the 3 coils, A, B, and C, and they get fed into this Clark-Park transform. And you also feed in the rotor position using an encoder or a resolver on the back of the motor.
Do we need absolute position here or relative position? Does that need to be an encoder or a resolver?
So you can do it with an encoder with an index pulse. So an index pulse will pulse once every revolution, and that will like reset it every time. You can do that, or you can use an absolute method like a resolver.
Would you need like absolute electrical position? So you need to know where it is in the electrical cycle. You don't necessarily need to know where it physically is. So you could, for instance, align it with the pole at the start and then just measure incrementally from there and work it out. But you do need to know where it is relative to the like electrical frame of the stator, because otherwise you'll be like out of sync.
But if the motor doesn't start at that index pulse, then will you need to like perform like a homing routine?
Yes.
So 0, yeah.
Exactly.
Yeah. So it is handy to have an absolute, but that homing routine is actually quite easy to do.
You just power one of the coils and it'll zip over. So we get our current from our 3 motors and our rotor position, and this box spits out the direct and quadrature signals. And then, as Dory pointed out before, we the notation, the block diagram notation here basically represents that we want to drive the direct signal to be 0. So a PI controller is designed to drive any input it gets to be 0. So it will adjust the direct voltage so that the direct current goes to 0. And similarly, the quadrature current will be PID controlled to be whatever quadrature current we want it to be. So some non-zero value, say 1 amp. And the PI controller will adjust the voltage of the quadrature voltage to achieve that goal. Now you're probably asking, what the heck is quadrature voltage and direct voltage? We're so far removed from the coils right now, I have no idea what's going on. Well, then you put it through the inverse Park transform, just the Park transform, and that gives it back into alpha and beta. And then there's this box called the PWM generator, which I'll get to in a moment.
That's a fun box.
This is an interesting box. Now, does anyone have any questions on all of this control loop part?
Yeah, I also had a question on the Clark Park, like green box. There. Is that a Park transform, then a Clark transform?
It's a Clark, then a Park.
It's a Clark, then a Park. So it goes into alpha beta and then into direct.
Yeah. Okay, cool.
So you just go from 3-phase to just 2 phases 90 degrees apart, and then you just rotate them to line up with the rotor.
Yep. Cool.
I keep racing ahead of my slides and talking about stuff before I have the slide for it, but this is what I just talked about. And as I said earlier, it's much easier to control these steady state values that don't vary much, because we're always trying to drive the quadrature, sorry, the direct current to 0. We're always trying to drive the quadrature current to some value. So whereas before we were trying to control oscillating things, which is just really hard to do. So yeah, then we put it through the inverse Park transform, and that gives us the alpha beta voltages. Cool. All right, now this is the last hard thing, I promise. This is called space vector PWM. So SPWM or SVPWM. It sounds more scary than it actually is. But this is basically, before I waved my hands and I was like, we can generate any arbitrary magnetic field that we want in any direction. But now I return to the question, how do we actually do that in practice? And how do we do that to get any length magnetic field or any magnitude magnetic field and any direction magnetic field? And to be honest, it's been a while since I looked at this and I'm a little rusty. But basically we have there are 6 states on the circle here. So same by energizing each of exactly the same as trapezoidal commutation. We energize each of the coils and we get 6 different states. But now we also have the option of the 2 null vectors in the middle. So if you turn all of the top row off or all of the bottom row of MOSFETs off, then you get no current through your coils. So yeah, basically you can see here the red ones are, I think, on. I don't actually, probably doesn't matter. So here, say white is closed, or you reckon red is closed?
Red's the on switch.
Okay, red's on. So in this example, we've got current flowing into the A coil, and then it goes through our motor and back, and then it flows out of the B and C coils evenly. And say this one, current flows into the, actually I'll do this one. Current flows in through the A and B coils, goes out to the motor, and then out through the C coils. So you can picture with this diagram here, if we toggled between these 2 states at a really high frequency, all we would be doing, so this is 110 and 100. So that's this one and the one above it. So if you look at the difference between these, the only difference is we're toggling the MOSFET above and below the B coil, the B input. So all you have to do is toggle that back and forth, and you'll generate a magnetic field that is this red vector here. So you add these together and then halve it, and you get that red vector there. Does that make sense?
Wait, so we're toggling A and B not at the same time, but they're so fast that
yeah. So we're PWMing between them. So for half the duty cycle, you get current flowing. So all the time you have current flowing through the A coil and out through the C coil. But half the time you have current flowing in through B, and half the time you have current flowing out through B. So this B polarity sorry, these letters here are not matching these letters here. Sorry if that's confusing.
No, it's okay. They match the one to the right at the top.
Yeah, ignore these letters. Yeah. So yeah, essentially you're toggling between no, I'm getting lost as well.
This is a really confusing thing, but the easiest way to think about it is what you actually need. So when you're implementing this in hardware, this was the way that it made it all click for me. You don't want, I want to be in this state, I want to turn this on. What you need is an on-time percentage for each of your H bridges. You need to know how long should this one be on and whether it should be high or low. So you basically want to work out what's the on time for each of those 3 half bridges. How long in this cycle should it be on? So the way to do that is to go, all right, well, what are the things that I can actually do? I can put the currents in such a way that I can get any of these 8 states. That's all you can do. So those are your pure states. If you were to leave something on 100% of the time and off the rest of the time, in say V1, so your A high sides on and then your B and C low sides are off, then you'd get a vector pointing along V1 in that diagram on the right. But what if you want a diagram that's something that's in between V1 and V2? Well, for half the time, you need to end up being in the state of V1. In half the time, you need to be in the state of V2. So you look at that. That means switch A needs to be on 100% of the time. Switch C will be off 100% of the time. And switch B will be on for 50% of the time and off for 50% of the time. Then if you actually need a vector that's a little bit closer to V2, then you would have it so that B stays on a little bit longer than it stays off. And then what if you don't want full power? That's the magic one. That's where the null vectors come in. So if you don't want it to be on all the time, so say you want 50% total duty cycle, then you actually want it in the null state for half the time. And then the rest of the time, it should be in one of those other 2 states. So basically you pick your direction by taking 2 of the main 6 states, and then you add in a certain amount of time in the null state for your off time. And then you literally just add up the time. So if you end up adding up, you need to be in V1 for 25% of the time, V2 for 25% of the time, and V0 for the rest. Then you literally add up the on times. You go, well, A is going to be on in both V1 and V2, but off in the null state. So that'll add up to A being on 50% of the time. So there's your duty cycle for A. B needs to be on when it's in V2, off when it's in V1, and off when it's in V0. So then you need it to be on 25% of the time. And C is off in everything. So it's just 0% duty cycle. And that actually gives you the duty cycles for what you want to do. So it's basically a way to take that arbitrary vector and work out what duty cycle you keep the switches on in that cycle.
This is crazy. This is actually
it's cool, right?
This is ingenious, but it is not clear. If I were to design this, that I would expect that, if I pause at any time, there's no, it's just in one of the 6 states or one of the 8, but
you always average it. It's always averaged.
Yeah.
With this kind of stuff, you can only ever be on and off. MOSFETs suck at being halfway, because if you're getting half the power through a MOSFET, that means half of it's being dumped at here. So you really want it to be on or off, and then you change the amount of time. So this is basically just 3-phase PWM.
What might help, Alex, is the fact that because they're coils, they actually resist changes in current, right? They're inductors. So even though we're switching between all these states, the actual current flowing through the coils is effectively constant. Right? Because we're switching so quickly that it's just zigzagging like that, right?
Yeah.
And that's exactly what we want. We want a current, because if you look back at this, we're doing current control. That's what we're doing. So that's what we want to do.
Yep. You run your PWM, or in this case, your state vector PWM, fast enough that the current barely changes. It doesn't have enough time to change. You're running it so quickly that the inertia of the inductance, it'll go down a little bit, but then by the time it goes down a little bit, you're in the next cycle. And it only ever ripples by a couple %.
Yeah, we may be talking about switching between states and creating 2 magnetic fields and switching between them, but we're actually we are creating a magnetic field in that direction. Physically, that is what's happening. So yeah. Okay.
Because of the inductance.
Exactly. Any other questions on this stuff?
So in between,
Taha, you go.
Just a quick one. In the between states, is it weaker? So if you were to, instead of driving it at ABC, if you were to consistently drive it in the between them, would you be looking at, would it be weaker or?
So you wouldn't ever only drive them in 6 states that are now like between the old 6 states, you would drive it smoothly between as a 360. So you'd be creating a magnetic field that is always like continuously changing.
Okay, yeah.
But it won't, theoretically, it won't end up being weaker. It'll end up being the same strength, just in a different direction.
Yeah.
So yeah, you can get the same amount of torque at any position. That's why field-oriented control is kind of magic. It doesn't matter if you're between like stator poles, you should still be able to get the same amount of torque.
Yeah. Jerry?
So if you did that, if you did that and then use the null vectors more, would it decrease the power or?
Yeah.
no?
Yeah.
Yeah, it would decrease.
Ah,
It would decrease the PWM voltage, which would lower the current.
Yeah.
Right,
So
cool.
if you think about it, have you seen like a normal H bridge?
yeah.
So in a H bridge, it's basically the same thing as the state vector, except you don't realize it because it's much simpler. So your states are either, or your useful states are either high side on one side and low side on the other, or low side on the first side, high side on the other. And then if you've got both high or both low, that doesn't do anything. That's a null state. So the way you PWM a H bridge is by turning, if you want it to go forwards, you might have your A phase powered on and your B phase off, but then you'd actually only have your A phase on half the time because you need a 50% duty cycle. So really you're keeping your low side fed on B and you're just changing A between on and off. But that's the same as going into a null state. It's just there's only 2 non-null states for a regular H bridge. There's 6 non-null states for 3-phase space vector PWM.
Nice. Cool stuff.
right. Jerry? Oh, are you there? I think Jerry might be dead. All right. While Jerry recovers.
Aidan, I believe I believe the voltages will actually be
I think this might have
square
been
waves.
covered, but I missed it.
Oh, why 90 degrees for max torque? Easiest way to explain that is to go all the way back to like slide 2. We've come a long way. Coils, your magnetic field, your torque is maximum when this red arrow is perpendicular to your coil.
The red arrow though is the force.
Yeah, you're right. Sorry.
That's different.
You are correct. I should be saying force. Actually, okay.
So my question is, why does the 2 magnetic fields need to be at 90 degrees? It feels like it should be related to the Lorentz law, but that's to do with an electric current and a field.
Basically, you want, yeah. So they're at 90 degrees when. How do I explain this?
Think about like a physical magnet, right? If you've got 2 magnets and the north poles are facing each other, or the north and the south poles facing each other, then you'll get a lot of force between them. They'll be pulling directly together, but there's no component of that force perpendicular, so they won't rotate.
Yeah.
Whereas if the south pole is 90 degrees, so if you start rotating it from flat up to 90 degrees, now there is no component of it pulling them together. It's all perpendicular and rotating it. So it means the maximum amount of the magnetic attraction force is going into rotating it, because your torque will be most effective if it's perpendicular to your lever arm and not to just like pulling against it.
Yeah, that's a good explanation. Not only does
That make sense?
not only does it being 90 degrees mean that one side is attracted to the magnet, but the other side is also pushed away at the same force. So yeah. Yeah, Aiden asked, I know you answered this already, Chris, but I'll go over it. What would the voltage on each coil look like on the oscilloscope? It would average out to a sine wave, but isn't that a simplification? Yeah, so basically it would be like horrific like square waves that would increase in frequency as you get close to the peak and decrease in frequency as you get close to the zero crossing, and then go negative for the other side.
Yeah, your voltage will always just be a PWM square wave. The voltage doesn't really get smoothed because there's no capacitance involved.
Yeah.
It's just the inductance, which only smooths out the current.
Cool. All right. So now, how do we velocity control this thing? So we've got current control, or torque control, as you might say, because torque is proportional to current, vice versa. So I've kind of drawn over this. In the original diagram, we had our IQ reference. Now we put the entire thing inside a velocity control loop. So we have our target speed, and this is all just a giant black box, and then the motor spits out a measured speed on the encoder. So we could use the quadrature signals from an encoder to do this. And you feed this into your PI controller, and the PI controller will adjust the current to get it to drive at the speed you want. So it's slightly different to before when we were talking about adjusting the voltage. This is adjusting the current. This is actually how you're sort of meant to do it, but we don't on the CMDs. But yeah. Then, yeah, what if you want position control? Well, you can do exactly the same thing. You can put the entire thing inside a position control loop. So you just need some sort of angular knowledge of the whole joint. So for example, the arm, you put a resolver on the output of the arm, and then you can drive the joint to be whatever position you want it to be. And you do this by changing the target speed, and then it filters through, and it gives you a target current, and it gives you, well, it goes to all this, blah, blah. You could also do this to get the rotor in a specific position. So if you Google, there's some really good videos of people who like use hobby grade, or like make their own brushless drivers. And the driver is just like spinning at a really slow speed, and then it like stops. And you can really easily change between a position control, a velocity control, and a current control loop. Because compared to a current control loop, a position, like once you've got that, you kind of already have all the things you need to make a position and velocity control loop. So it's not that much harder to do. And yeah, I was saying you could put a resolver on the output of the arm joint. You could also put it on the input shaft of your motor, and control your motor precisely if you wanted to. For example, UAS, to be honest, they probably don't do this with a position controller, but when they switch from VTOL flying to forward flying, they want to put their rotors in line with the drone instead of perpendicular, because it's got less drag. So if you wanted to, you could switch to a position control loop and then rotate them to be in the right position. Realistically, they probably just do that by magnetizing one of the coils.
I'm pretty sure they
have to pulse
it.
Yeah, they have to pulse it because, like, electrically they know where they are, but mechanically they don't, right?
Yeah, well, yeah, they have no sensors either in UAS. It's probably a shit example.
I don't think they use a BLDC to do that rotation. I think it's just a servo.
No, they actually spin the motors. Anyway.
Yeah, I believe they pulse it and they detect whether or not it's in the right quadrant or not. And they skip to the next one if it isn't.
Cool. All right. So here's a big table of everything. So to summarize, we don't know trapezoidal method. So this was not using back EMF. This was not using any encoding. Sucks at very low speed, sucks at low speed, works at middle speed, doesn't work at high speed. There's lots of torque ripple and is not efficient. It's just bad. Don't do it. Back EMF trapezoidal. This is for drones, so it works at middle speed, works at high speed. Still has torque ripple because they're still using trapezoidal commutation, and it's reasonably efficient. And we use the fact that the back EMF, because the back EMF is proportional to voltage, is why it doesn't work at low speeds. Hall effect trapezoidal. This works at low speed, so say like, maybe like a couple of times a second, or maybe like one revolution a second sort of speed, because we can sense the magnet position using the Hall effect sensors. Works at high speeds, works at middle speeds. We still have torque ripple because we're still using trapezoidal commutation. It is reasonably efficient, but we're always going to have that cos30 error, or up to cos30 error, because we've only got the 6 states and the rotor could be up to 30 degrees away from our magnetic field. Next,
does trapezoidal for back EMF trapezoidal and Hall effect trapezoidal?
Yeah.
Do trapezoidal actually mean like different things here? Because for Hall effect, we've got the square waves from the Hall effect sensor that we're detecting.
Yeah.
For back EMF, we are detecting that trapezoidal back EMF.
So yeah,
Like
you're
for-
right. So the trapezoidal refers to the back EMF, but it also refers, but you get the back EMF gives you that encoding for 6 states, and that 6 states is also used in the Hall effect commutation. So it's also trapezoidal.
Right.
Yeah.
Yeah.
Trapezoidal usually just refers to only using the 6 output states to control it. It really, yeah, you can do trapezoidal control on a sinusoidal back EMF motor. It's just like it's also called 6-step control, which I find less confusing because
Probably
otherwise you get it mixed up.
Cool. Second last one. So encoder sinusoidal is what I called it. This is when we were measuring the position of the rotor, but we were using PID control loops to control the current to be an oscillating current. This works at like lower speeds and mid speeds, but doesn't work at high speeds because you can't track an oscillating value with a PID controller. And then finally, field-oriented control. It works at any speed you want, pretty much, that the motor can do. Has 0 torque ripple, and is very efficient because we're tracking those stable direct quadrature values instead of the currents themselves. And that's it. So I hope you all understand this diagram now.
What are the outputs from the SPWM generator?
So they are the 3 H-bridge PWMs, or half-bridge PWMs.
Would they be literally like 1-0 going really quick, or is it
There'll be
just the
duty
duty
cycles. So they'll give you a period that you need to keep the
Oh,
thing
sorry,
in high
yeah.
side on.
Sorry, yeah, they're duty cycles. Yeah.
Yeah.
Right, and then the microcontroller figures out the timing to make sure that, like, while one coil is on, the other's off, and
So
vice versa.
it's so basically if you're doing that kind of PWM, we didn't really touch on it here, but you use something called center aligned PWM, where you kind of like actually do the pulse in the middle, and then all the pulses are kind of symmetric. It doesn't actually matter if you're actually in one of those 3 states and when you're in it. You just need to have all the switches on the right amount of time, and through all the averaging, it just works out. So it's literally just a percentage of time that the high side switch needs to be on versus the low side. And you always have one of the 2 on. So you'll just get like a percentage for each of the half bridges. That's the amount of time they need to be on.
Right, and the specific sequencing of when exactly each one is on doesn't really matter.
Yeah, you just you do what's called center alignment. So I'm gonna find a photo.
Yeah.
Line.
I know what center line looks like for a single PWM line. I'm just not
Yeah,
sure
you
how
just
it
have
translates
3
to
of them
three.
that'll end up with different duty cycles.
The one thing to note, Jory, is so like when you're switching between your 3, like you'll only ever have 3 states you're switching between. You have a null vector and 2 other states.
Yeah.
The two states on the ring will always be 1 MOSFET different.
Yeah.
And the null vector will also only be 1 MOSFET different. So yeah.
And that's how you choose which null vector to use.
Yeah. So and I don't think it matters if you drive. Yeah. Anyway, I think I know what you're trying to get at, and I don't really know the answer, to be honest.
Right. So another thing, like for A, for example, in V1, they would always have either the top MOSFET on or the bottom MOSFET on. You would never do like both on or neither on.
No.
Correct. Both on would result in a short circuit.
Yes.
So
that
it would be very
obvious.
bad. And for these, you never do them. You never leave it closed, like with none of it on, just because you need current to flow through all 3. So during the off time, even while all 3 are off, because you've got like the inductive average current, it'll end up drawing current up from the like ground to make up for it, kind of like a buck converter topology. So it's important you always have them on. Otherwise, what happens is the low side MOSFET that probably should be on will end up conducting through its body diode, and it's way less efficient than having the MOSFET on, because there'll be a voltage drop across the body diode that's much larger than the voltage drop across the IDS on. So it'll be way less efficient.
Yeah, right.
Any other questions?
Might be a bit like not a specific answer, but like, can you do like braking and stuff with these?
Yes, sort of.
So not with like not with the half bridge, but by like driving it in the other direction.
Can't we just turn on use like
right, 'cause
torque
it's torque
control in
control.
reverse?
Right, that makes sense.
So yeah, torque control in reverse, basically.
Yeah, cool.
Yeah. So what'll end up happening is it'll end up putting power back onto. You can set it to do constant current in the opposite direction to what it's spinning, and it'll be acting like a generator. But it'll just be setting everything up so it kind of acts like a boost converter, boosting the voltage up to put it back on the bus. So if you're running off a battery, you can just let it go back into the battery. So you can just run it in reverse. If you don't have a battery, often there'll be like a separate braking resistor that you'll turn off when you know you're regenerating, because otherwise your voltage supply might spike and blow up your power supply when you start regenerating. But for us, because we have a battery, if it starts regenerating, it'll just end up charging the battery or powering other parts of the rover.
Sweet.
Any other questions? Any niggling questions from like slide 3 that you wanted to ask but didn't have the courage to back then? Or Aiden, you're going to say something?
Yeah, it was more of something that's not contained in this slide. In the past, Christos, you mentioned that like we want like pretty high resolution encoders and resolvers on this to actually sense like where we are in the magnetic field. Therefore, we can do the pulsing exactly right to orient the field at 90 degrees. What does decreasing that resolution of resolver actually physically do in terms of like performance at low, medium, high speeds as well as efficiency?
Yeah. So an easy way to think about it is when you're doing that like trapezoidal control, it's like you have an encoder that's only accurate within 30 degrees. So you can get up to 30 degrees of error in it. So if you have an encoder that's only accurate up to 1 degree, then you can have up to 1 degree of cause error. So once you get below 1 degree, you're basically fine because cause of 1 degree is almost nothing. So yeah, you need a.
Why do you want 2000? Yeah, why do you want 2000?
So the reason I want 2000 is because there's 24 poles on there, which means there's 8 electrical cycles per rotation. So you have to divide your 2000 pulses by 8, which starts looking less good. That gets you about a degree. Whereas if you have 1000, you're getting like well into like 3 degrees, I think.
When you say 1 degree, is that in the electrical cycle?
Yeah. So which would probably like it would totally work with 1000. To be honest, anything better than 30 degrees electrical will work better than trapezoidal. And there are diminishing returns after a point because eventually you know the error gets quite small. But the more accurate a position you have with that, the better. In terms of basically it's just that rotor position that feeds back into the Park transform. If you don't know your rotor position accurately, then you'll rotate your reference frames to the wrong spot and you'll be making a vector that's perpendicular to where you think the rotor is, but not perpendicular to where the rotor actually is.
Yeah.
But realistically, I'm being a diva. We could make it work with a lot less than that.
No, let's get those 12-bit magnetic resolvers.
Yeah, well, like even if those end up only being accurate to within like 5%, that's still more than enough for what we need to do. Probably not to be a resolver, but it'll be enough to do field-oriented control, which is why I'm pretty confident that we can use that as an encoder. Because like the way all these things you see online, if you see like these motor drivers that say they do field-oriented control and they use Hall effect sensors, the way they work out where the rotor is they figure out what their velocity is by counting the time between the 2 Hall effect pulses, then multiply it by how long it's been and try and guess where the rotor is going to be just based on like a Euler approximation on their last velocity, which works fine at medium speeds. But as you get really slow or to like static rotor position, like locked rotor, that stops working. So if you want to be able to apply full torque at 0 RPM at any angle, you need proper absolute positioning. You can't get away by interpolating off of the Hall effect sensors.
In practice, when we're implementing this, would you use the same encoder for rotor position, measured speed, and the position feedback?
You'll probably use the same one for rotor position and measured speed. For doing the position feedback, you might want to
I'm guessing you'd
use
have to
something on the
count
output.
revolutions.
Sorry, what was that?
I'm guessing you'd have to count revolutions, so you get the right number of electrical cycles for each physical.
Yeah, so you run into problems with zeroing and stuff when you do it on the input side.
Yeah.
Whereas if you have a resolver on the output side that can only like the arm joints can only go to 360, then you don't have a worry.
Like this.
What?
Okay,
All
another
right,
question.
Layla.
Yeah. I remember someone bringing that up in like a lecture and they get like harassed by the lecturer for it. Anyway,
The trick is I didn't go to lectures.
Is that why you did 1005 plus?
Yep.
I was going to bring up, you know, the PWM frequency in like a brushed motor is like fairly critical to like its rotor inertia, and like if you drive it too slowly, you end up with like stall characteristics at like when you try to turn it on, whatever. At what frequency would we want to drive the PWM driver in this particular like system diagram?
It's pretty much the same. You need to have your PWM frequency substantially higher than the electrical time constant of your your like windings. So yeah, see that
want to avoid this.
You don't want it to go all the way from 0 up and then back down. What you want it to do is be changing so fast that it barely has time to go down. So yeah, you want it to be substantially faster than the electrical time constant, which is a product of LR and a formula.
And is that going to be around the same range as like a brush motor?
Yeah,
where it's
it will be
you know,
around the same range.
a few kilohertz
Basically,
or something like that?
usually you just end up doing like 30 odd kilohertz or between 25 and 30 because you want to get it out of the audible range. And usually if it's that high, it'll be higher than your RL time constant. Yeah, so I'm at the moment aiming for around 25 kilohertz.
Piss
So
off
that's
all the
twice
dogs.
what we're doing right now.
Yeah.
Alrighty. Any other questions, or shall we wrap it up? I'll take the silence as a good sign that everyone's learnt a lot and is ready for bed, because I sure am. Cool. Well, to wrap it up, hope you learnt a lot, because I sure did putting this together, and I hope it made mostly sense. The slides are there if you want to go back through it. We'll put the recording up, probably on YouTube. Probably
I'm retiring. Who's doing my FYP for me? You all now understand, right?
Yeah. And a lot of this is covered on your Clino in text. So if you want to kind of get a refresher, you can look there as well. Maybe next week, I think, probably I'll be doing one of these on the CMDs. So stay tuned for that, I guess. Cool.
Well, thank you so much for putting this together, guys. It's been really informative. I understand a fuckload more now.
I didn't actually put it together. I
It was not me.
Bye, guys. Will.
I am more
You
than
answered
one person.
some of the questions. Thank you.
Yeah, well, I ran it by Christos and he gave it the thumbs up, so I thought that's a good sign.
And I did see some of the resources that were in my GAF OneNote make an appearance in the
Yes,
slideshow.
definitely.
My notes, see, I do notes too, but they're way less like good, and anyone else would be able to understand them than Will's stuff.
All right, I'll end the recording here.